Okay, so today we're going to talk about Unit 3, Energy Transformation. The things that we're going to be talking about are mostly mechanical energy. So like, the energy of moving things, or if I lift something high up, it's going to want to fall down. So what is energy? Basically, energy is a property of all matters. And the key thing that in physics term is that energy is the ability to do work or perform a task. Two main types of energy: potential energy and kinetic energy. And kind of one of the biggest word is potential energy is energy that are being stored, right? So energy that is like kind of when you do something to an elastic, say for examples, okay? And if I stretch it out, do you see how you're storing the energy called the elastic energy within the elastic? And once that let go, it can actually start moving. All right, so then it becomes kinetic energy, energy of motion. And some other things would be, say, chemicals. Within a battery, there are actually chemicals. I don't know if you've ever seen the inside of an alkaline battery. They actually have a positive and a negative, and energy is being stored there. And once it's hooked up, the proper way, if we complete the circuit, what happens is it's going to turn into, say, thermal energy because it's going to warm up, and radiant energy because it's going to light up. All right, so these are all the different types of energy that you could have. So you can have this in front of you. That's my suggestion when we do this thing called the energy transformation equation, which we will do later. All right, so what is energy transformation? When work is done, energy often change forms, okay? And the energy transformation is a word equation that describe the changes. And basically you would use these types of terms, right? Like these are the terms that we would be using when we're writing the energy transformation equation. So on the test, I would be like, write the energy transformation for whatever the object is, okay? All right, so let's do the examples together, okay? Write the energy transformation equation for fireworks. Okay, I don't know if you're aware, but fireworks basically happen when you have some chemicals and you light them up, and then they start shooting up into the sky, and then they start giving off color. So there's lots of process. Okay, so let's think about that. So we got these powder thingy, and we light it up. With that together, it's going to start to rise up to the sky, and then have explosion of sound as well as light that is going on in the sky. Okay, so I know my pictures are awesome. Okay, so the first thing is step number one. At the beginning, you basically would, I should go back to this table, right? So we have some chemicals that is waiting to happen, okay? So we have chemicals energy that is stored within the whatever the powder that they're using. So they're actually chemicals. So in the fireworks, the different colors are given by different chemicals. If you take chemistry, I don't know if you would have a chance to do that. If you actually start burning like barium salt or something like that, they'll actually glow at different color, and those are the color of the chemical burning, and that's what's inside your fireworks. Okay, so we have store chemical energy. Okay, and then with the chemical energy, what happened is we're going to put in the fire, which is the thermal energy, and then it's going to be transformed into, first of all, it's going to start moving, and so it's going to have mechanical energy that is now shooting, is moving. So I'm going to have mechanical energy. And then once it gets up to the top, I'm going to have to erase my picture. Once it gets up to the top, what happened is it's going to start exploding. And what happened is it's going to get really hot. Like it's going to be very hot. It's heat, and it's also going to give off light. And I don't know if you remember, fireworks also give off sound. Okay, so then it becomes sound. Oh my goodness. Sound plus thermal plus radiant. Okay, so that's the energy transformation equation. All right, second one, battery operated flashlight. So you have battery, and the battery is hooked up in a circuit. And in the circuit, your flashlight then give off light as well as heat. Right, so we start out with the battery, so we have chemicals again. And then the chemical energy is now hooked up to the battery. It becomes the electrical, because from the chart here, you have an electrical energy right here. Okay, and then from the electrical energy, it is now going to be giving off light, which is radiant, and heat, because your flashlight do warm up. So then you got thermal. All right, so that's the first type of examples of questions that we can ask you from lesson 1. And then the second type of question is actually dealing with work. It's an equation. So work is the energy transferred by a force over a distance. Okay, so as the equation say, work is force times displacement. And force is in Newton. We know that. Displacement is measured in meters, and work is something new. It's measured in joules. Okay, and so they give you the magic triangles, and you know how I always suggest you to write out all possible form of the equation if you need it. Some of you are getting better at rearranging equation. Like if I say what's F, and without looking at the magic triangle, some of you can quickly say, well, it's W divided by D. But if you still need the magic triangle, use it, right? Because you don't want to make a mistake. Okay, so let's do what I always do. I always draw a shape just to cover this up. So if whatever things I'm looking for, I would cover this up. And so say if I want to work out for work, I want to find work. So F is beside D, so it's F delta D. If I want to change this and say, hey, I want to look for F, I'm going to rewrite the equation for F. W is at the top, D is at the bottom. Okay? And then if I wanted to find D, delta D, then W is at the top, F is at the bottom. All right, so that's just the different ways depending on what the question is asking for. All right, more definitions. So these I would assume it to be a multiple choice types of question or written types of question. Okay, there are 3 types of work: positive work, negative work, and zero work. Definition. Okay, what does it mean by positive work? Is when the force is in the same direction as the displacement. Okay, what that means is if I have a block and I push it to the right and the object is moving to the right, then I have a positive work. If I'm looking at force of gravity and the object is being dropped downwards, I have a positive work when the force and displacement are at the same time. Okay, I'm going to be tricking you now because we're going to go to the second one. Second one is when the force is opposite to displacement. Without giving you an example, and I'm like, you, tell me an example of a force that is opposite to displacement. Can you tell me? All right. A big example. Let's see if you can think of it. Force of friction. Okay? If I have a ball and I rolled it along the ground, I tossed it, I'm not pushing on it anymore. There's no more applied force, and the ball is like sliding to a stop. Okay? Do you see that the object is traveling to the right, but the actual force acting on it is actually force of friction that's causing it to go backwards? Like, no, that's causing it to slow down. All right, so friction is a really good example of when we're talking about the force opposite to the displacement. Okay, last type of example or definition is if I have zero work. Zero work is when the force is perpendicular to the displacement. Okay, there's 2 examples, but I'm going to say the first one. Anything in a circular motion. Okay. If you're going in circle, you're already going in, you can already say that it has to be 0, okay? All right, the second example of a force that is perpendicular to a displacement, we call this the waiter, okay? The waiter effect. Okay, you'll be like, huh? Okay, if I have a waiter and he's serving this guy who wants his chicken, okay? Okay, the waiter is holding the chicken up like this. This is my chicken that he's delivering, okay? No, the leg. I don't know. This is whatever he's serving, okay? The way that he's holding the chicken is you can see that his hand is moving upward. Like he has to hold it up. Is that fair? You can call it FA or FN, right? The holding up force of the chicken. But the guy is walking towards this way. Do you see that you're walking this way? So this is an example of zero work done because the FA is 90 degree to the displacement. The chicken's moving to the right, but the force holding up the chicken is up, right? So you carrying your backpack, walking down the hallway. Do you see how you're walking down the hallway? And then you carrying your backpack. Okay, I'm going to try to draw a backpack. Your backpack is here. See how your backpack is held up by this strap. That is FT. But you are walking this way. Okay, same thing. Zero work are done. Okay, finally, the last type of thing that we're going to talk about, it is a review. Okay, but this is, you know how we said work is F delta D. But sometimes if I am raising an object, okay, what happened is you need to understand that the force is actually the amount of force for you to go against the gravity, okay? So that's why they're saying if I am raising, like lifting some object up, so I'm lifting or lowering actually. So if it just goes straight up and if the object is going straight up and down, and I want to know what is the amount of work done if I lift it by 5 meters or something like that, it is M times G. So you can almost group it together. It's M times G delta D if I'm lifting, okay? But you can just always just start out with this and then knowing that, oh, FG is M times G because you already learned that. All right, finally, there's a law of conservation of energy, okay? And it's a law that we use in physics all the time. And they're basically saying that all the energy in the universe is constant. And so kind of like the energy equation we were writing, like say this, we didn't get the light from the flashlight free. It got converted from a chemical energy, right? And that's kind of where the law is leading to, is energy can only be transformed from one form to another, but it will never be created or destroyed. Okay, so at the end of the day, your total energy in the system, it's always going to be the same. You just convert from one form to another. All right, question 1. A store employees exert a horizontal force of a magnitude of 44 on a set of carts. How much work is done by the employee by pulling the carts for 15 meters? So they tell you FA, the amount of force is 44 Newton. Okay? One thing is recognizing the unit again, right? Delta D is 15 meters. Are we okay with that? Because it moved for 15 meters and they're asking for what is work done. So we know that work is force times displacement. If you need to, you look back to the equation, right? Okay. Force is 44 Newton. Displacement is 15 meters. So this time I multiplied. So 44 times 15, 660. Unit for work, what is it? Joules. Next one. Okay, a 20 kilogram crate, that's my mass, is lifted, I'm lifting something from the floor to the shelf 1.5 meters above. Calculate the force needed and then how much work. Okay, so I have mass of 20 kilogram is lifted from the floor. The displacement is 1.5 meters. Part A wants you to find what is the force, and part B wants work done. Okay, so equation for force, when I'm lifting something up, we already talked about that. When I'm lifting something up, I just use the Fg, the force, to go against the gravity. Okay, so Fg equals to m times g. So you write your equation out. So 20 is the mass. I do like to put the unit. 20 is the mass. And okay, are we okay with what g is? We've done it so many times. It's 9.8, okay? 20 times 9.8, 196 Newton. Okay, force is measured in Newton. And then now that I have the force, I know work is F delta D. So F is 196. And delta D, I've moved it for 1.5. So times 1.5, 196 times 1.5. So 294. What's the unit for work? I hope you know it. All right. Last one. A tobogganing carrying 2 children, a total mass of 85 kilograms, reaches its maximum speed at the bottom of the hill. It then glides along the horizontal surface and comes to a stop in 21 meters. The coefficient of kinetic friction, do you remember that term? The coefficient between the tobogganing and the snowy surface is 0.11. Draw the free body diagram for the tobogganing when it's, so I need to draw the free body diagram when it's gliding on the horizontal surface, okay? All right, so on the ice, we always draw a free body diagram with FG. I think that's pretty easy because it's sitting on the ice. I have upward holding force going like this. Okay, keyword is gliding, okay? I'm no longer applying the FA, okay? So that means I would have one force that's going backward, which is F. Calculate the magnitude of the force of kinetic friction. So they want you to find what is the force of friction. Okay. So this is part A. Okay, part B, I haven't listed everything. I know M is 85 kilogram. And they gave me displacement is 21 meters. And I would like you to calculate what is kinetic friction. So F. Ooh, do we remember how to do this? All right, what's the equation for kinetic friction? Yeah, got it? If you need to go back, you can go back. Equation for FF is mu times Fn, okay? Coefficient of friction times force of normal. You don't have your force of normal, but you can find your force of normal. I don't know if you remember. You study the forces along the y, okay? Basically, in cases like this, your Fn equals to your Fg. Remember, your up equals your down because I'm not accelerating along the y. So I know the equation for F times G is mg, so I can plug in my mass and I can multiply it by the 9.8. So 85 times 9.8. Ooh, good question. Do we remember? They come back. They don't go away. Okay, so first of all, work out what Fn is. Fn is 833. Then what I can do is now I can throw this number into this Fn, right? And I already have mu. I don't know if you remember. Am I going too fast? Do we remember that coefficient of friction is the unit, the little symbol for mu? I didn't write it out as my given. Do we remember coefficient of friction has a symbol of the mu? Okay, so it equals to mu, which is 0.11 times the force of normal that we calculated here. So 833. Okay, so times 0.11. So this equals to 91.63 Newton. Okay, finally, they want you to calculate what is the work done by the friction. What is the work done? Okay, now this is tricky. Okay, this one is probably the most tricky question. Well, sort of. Okay, so part C wants you to find work done. Okay, I know the equation for work done is F delta D. But the only thing I need you to be careful is that, don't forget, my displacement is going to the right, right? I'm still gliding to the right, but my force of friction is backwards. I don't know if you remember that you've learned that if my force is opposite to the displacement, I have a negative work done. So you actually need to stick a negative in here because it's a negative work done, okay? I'm just going to make a little note. So negative work done since the force is opposite to the displacement, okay? So I have to stick a negative in front of here. All right, so now it's just math. So negative work, the force is 91.63 that I got from the last question. Displacement is 21. So 91.3 times 21. So my answer worked out to be negative 1924.23